Hi everyone. Today we're going to talk about the Riemann Rearrangement Theorem and concrete illustrations of it. This video has some nuts and bolts proofs and is aimed at people who have had at least a semester of undergrad real analysis under their belts. First, a little bit of background. This is the alternating harmonic series, and it's a standard example of a conditionally convergent series and among the first that people often see in a first-year calculus class. Though why it's interesting isn't usually discussed at that point because it's not level appropriate. The alternating harmonic series can be used to illustrate the Riemann rearrangement theorem, a version of which states that the terms of a convergent series can be rearranged to sum to any preset value if and only if the series is conditionally convergent. What we're going to do is review the proof of the full Riemann rearrangement theorem and take a look at a concrete, countably infinite set of rearrangements inspired by its proof. Then we'll apply this class of rearrangements to the alternating harmonic series and similar series after that. These rearranged sums are very concrete and easy to describe and compute. Also, for a given initial series, the set of values of its rearrangements taken together is dense in the set of real numbers. Of course, we're only talking about a countably infinite set of rearrangements, so it can't possibly be the entire set of real numbers, which is uncountably infinite. But it certainly illustrates the spirit of the rearrangement theorem. Here's the Riemann rearrangement theorem, published by Bernard Riemann posthumously in 1866, though a bit of digging shows that he actually deduced it in 1853. Starting with part A, let the sum of A sub j be absolutely convergent. The following holds for every permutation sigma. Basically, this means that no matter how the terms of the sum are rearranged, the value is the same as the original sum. This ability to rearrange absolutely convergent series underpins many intuitive manipulative results in analysis that can be false if we try to apply them to conditionally convergent series. Part B explains how things can go awry if we throw out absolute convergence. Let the sum of A sub j be conditionally convergent and let L be a real number. There's a reordering or permutation of A sub j such that L equals the sum of this reordered sequence. This is one of the first results that flies in the face of the intuition students have usually developed, but the proof is relatively straightforward. Given a sequence A sub j and a prescribed limit L, it provides an explicit recipe, in principle anyway, to get the desired rearrangement of A sub j. Let's start off with the proof of part A. Step 1 is to verify part A in the case where the terms of the sequence are non-negative, called B sub j here instead of A sub j. First, define f to be the supremum of the set of all finite sums of terms of the sequence B. Since the sum of B sub j is finite, then f is also finite because each finite sum of terms of B is less than some partial sum of this original series. Looking at the infinite permuted series, since the values of B sub sigma j are all positive, we know it's the supremum of all of its partial sums. By the definition of f, this supremum is certainly less than or equal to f, and it's also greater than or equal to f because every finite sum is less than or equal to some partial sum of the permuted series. For step 2, we're going to write the permuted series, the sum of A sub sigma j, as a difference of non-negative sums and apply step 1 to each sum. This first line is clear. Then in the next line, we replace sigma j with j by step 1 and recover the original series. Here's a slightly abbreviated proof of the more interesting part B. First, we're going to create two sequences B sub j and C sub j. B sub j consists of the non-negative terms of A sub j, and C sub j consists of the negative terms of A sub j. Since the original series converges, we know that B sub j and C sub j both have zero limit. And since the original series isn't absolutely convergent, we know that at least one of the series formed from B sub j and C sub j has to diverge. If exactly one of these series diverged, then the original series couldn't converge in the first place, so they both diverge. This means that b sub j sums to infinity and c sub j sums to minus infinity. How do we build our permuted series? Well, without loss of generality, we add terms from the series of b sub j until the sum is greater than L, and then add terms from the series of c sub j until the sum is less than L, and repeat this process. We say without loss of generality because it could happen that we need to subtract terms initially rather than add them, but the idea is the same. Now, this step can always be iterated because no matter how far above or below L we are after a given iteration, by 2 we can always take terms from the correct divergent series to cross L again. The resulting sum converges to L because the overshoots and undershoots have limit L, since b sub j and c sub j have limit 0. We've proven part B, but the overshoot-undershoot method is pretty flexible. It can be used to make rearrangements whose partial sums oscillate as badly as one can think. Given the proof of the Riemann Rearrangement Theorem and an arbitrary alternating conditionally convergent series, it is natural to consider the sum of the first p positive terms and n negative terms, plus the sum of the next p positive and n negative terms, and so on. This leads us to investigate the limiting behavior of the following sequence of sums. After we iterate this first step k times, this is the sum of the first pk positive terms, plus the sum of the first nk negative terms of the alternating series. If we take a look at the thumbnail, it corresponds to a sub j being the harmonic sequence 1 over j, where p equals 3 and n equals 2. Note that the general permuted sums are all well defined, even if a sub j isn't always positive. In this case, the upcoming theorems still work, we just lose the interpretation of adding p positive terms and n negative terms. This is the first rearrangement result that pertains to the alternating harmonic series. The limit of this sequence of partial sums for a particular p and n is this simple formula. Here, recall that natural log of 2 is the value of the original alternating harmonic series. And note that this applies very simply to the thumbnail example. This result is very interesting because the value of a given rearranged sum depends only on the ratio of p to n, and there is no reason to expect such a simple relationship beforehand. Also, since natural log of q plus is dense in R, where here q plus is the set of positive rational numbers, the set of values of rearrangements is also dense in R. As an aside, this theorem was proven by Martin Ohm in 1839. This is the physicist Ohm, who has a unit of electrical resistance named after him. His proof involved a lot of power series manipulation, and is more complicated than the one we're about to present. I haven't tracked down the original appearance of the one here, but it's pretty old. What's coming up is a bit speculative, but the dates line up, and I think it's very likely, if not almost certain, that Riemann knew this result, and that it fed into the intuition that led to his rearrangement theorem. I find this interesting because these days, when a student learns about Riemann's theorem for the first time, they generally haven't seen a body of less general but illustrative results to motivate it. They just plunge forward with the general formulation and study the theoretical fallout. To contrast with the time prior to Riemann's work, it was already well established by example that some series couldn't be arbitrarily rearranged without changing their value. The general theory behind it just wasn't established yet. If anyone watching this has light to shed on the history, I'd love to hear about it. Moving onward, a useful tool for us is the logarithmic approximation of the harmonic series. So we don't have to keep on saying sum of the first n terms of the reciprocals of the integers to find the nth harmonic number in this way. Plain old single variable integral test estimates show that the sequence h sub n minus 1 minus natural log of n is increasing and bounded so that this limit is well defined. This value is famous and well studied, and is called the Euler-Mascheroni constant. The following more useful formulation is given here as equation 3. This little o notation is just a placeholder for an additive term that decays to zero as n, or whatever variable of interest, goes to infinity. It's a way to de-emphasize small terms while acknowledging their existence. The Euler-Mascheroni constant appears all over the place. It pops up in the study of special functions in complex analysis and in number theory, but we'll just use it to evaluate series rearrangements. To prove theorem 2, we're going to relate these partial sums to the harmonic series and use equation 3, the harmonic series logarithmic approximation. What we do is add the first pk even terms into this sum and then subtract them off again so that we have a linear combination of harmonic numbers. What's nice is the sum of coefficients add to 0, so when we use equation 3, all the Euler-Mascheroni constants cancel and we get this simple term. Also, this proof doesn't assume the value of the alternating harmonic series. Rather, it's deduced from it as a consequence when p equals 1 and n equals 1. We can generalize theorem 2 to theorem 3 for series that are approximately alternating harmonic. I'm not sure who came up with this beefed up statement originally, but I ran across it as a homework problem in an old analysis textbook published in 1928. Here it goes. If we have an alternating series of real numbers that converges to some limit s, and the limit of j times a sub j is L, this is where the series is approximately alternating harmonic, then the following holds. The permuted sum is the original sum plus the rescaled term from theorem 2, and we can directly compare the difference between the rearranged sum and the original sum. As a cute example, we can apply theorem 3 to Leibniz's formula for pi, where L is 1/2. It's worth noticing that if L is not 0, then the series converges conditionally. Just use the ratio test where the sequence of comparison is 1 over j. And the general comments after the statement of theorem 2 apply here as well. Now, if L is equal to 0, then the original series can be either absolutely or conditionally convergent. Take a sub j equals 1 over j times natural log of j plus 1, so that the nth partial sum of the absolute value tracks with natural log of n. Regardless, the rearrangements don't scramble the terms enough to affect the value of the rearranged sum. We can prove theorem 2 by a different method and adapt that to prove theorem 3. Instead of relating the sum of the first pk positive terms to the harmonic series, we can relate it back to the harmonic alternating series. Here, let S sub n be the nth partial sum of the alternating harmonic series. To the red term, add the first pk negative terms and subtract them off outside the sum. This gives the 2pkth partial sum of the alternating harmonic series plus a linear combination of harmonic numbers. As before, apply the logarithmic approximation to get the result. Taking limits, we can compare the permuted and original sum even without knowing the value of the original sum. It's not difficult to tweak this argument into a proof of theorem 3. Proceeding as in the alternative proof of theorem 2, take the sum of the first pk odd index terms, subtract out the first pk even index terms, and add them back on the outside. The first sum is the 2pkth partial sum of the original series. The near harmonic nature of a sub j means there exists a sequence epsilon j going to 0 such that a sub j has this form. Applying this to the second and third sums implies the following. Using convergence of the 2pkth partial sum to S and equation 3 gives us this result here. As a last step, we can estimate the remaining sums by again using equation 3 and the fact that epsilon sub k decays to 0. The difference of these sums is, up to a sign, part of the tail of a series where the smallest index bound increases as k increases. Now we just distribute the absolute values and pull out the supremum of the epsilons over the lowest index to infinity, leaving a difference of harmonic numbers inside an absolute value. Finally, use equation 3 to estimate the difference of harmonic numbers, and the fact that epsilon j decays to 0 to show that these sum terms here are a little O of 1. That wraps up the math. Thank you very much for sticking around to the end. This video was a lot of fun to make, and I hope you enjoyed watching it. Let me know what you think in the comments, and if there is any topic in particular that you'd like me to do a video on. Again, thanks for watching, and have a great day.